Okay, looks like we're rolling. And again, I'm going solo today. I have no camera operator. I'm literally talking to an empty room, which is a little bit new for me, so bear with me. What we're doing today is we're wrapping up chapter 5. We're going to finish that lecture. And where we left off was multiple examples of circular motion and how we can use what we know about the dynamics of circular motion to solve interesting problems. And in light of that, or related to that, let's talk about Ferris wheels. Okay, so Ferris wheels are an interesting example of circular motion in action. So what I want you to imagine here is a Ferris wheel that you're riding on that moves at a constant speed. So it doesn't speed up or slow down, it's just rotating at a constant speed. But by now we should know that if your body is moving in a circular path like this at a constant speed, it's still accelerating, and there's still a net force acting on it. And that net force has to be, at all times, pointing towards the center of the circle. Okay, so the net force on your body is always pointing towards the center of the circle. And as we've seen in previous examples, the magnitude of that net force is n times v squared divided by r, because v squared divided by r is our acceleration, our centripetal acceleration. But the net force is nothing more than a sum of all the different forces acting on your body. So if you're sitting in a seat like this, there are 3 forces that we have to consider. The first one, the most obvious, is gravity, or the weight. So the force W in these diagrams is going to be shown with the blue arrow always pointing downwards for the weight. The other thing that the seat can do to you is push up with a normal force, which we call N, and that's going to be shown with the green arrow in all of these different diagrams. So we have an upward facing arrow from the seat representing the normal force for all these different diagrams here. And the last one is static friction. Okay? In addition to a normal force, the seat that you're on can also potentially exert a force of static friction, which can keep you from sliding around back and forth in your seat. Okay, so in light of the fact that the sum of all these different forces always has to be pointing inwards, let's see what this looks like at different points in the ride. Let's say we're at the bottom of the ride over here. The weight is going down, the normal force is going up. I'm showing the normal force being greater in magnitude than the weight here, which makes sense because overall the net force has to be pointing in. The only way for that to work is for the normal force to be bigger than the weight. I'm also not showing a static friction force at all because that can only point either to the left or to the right. It would be a horizontal force. And if the net force is going in, there's no room for a horizontal force. That has to be gone. That has to be 0 in this diagram. And at the same time, let's say we're at the top of the ride. Again, we're going to have the weight going down. We're going to have the normal force going up. But the sum of those 2 forces has to point in towards the center of the circle. The only way for that to work is now the normal force is a lot smaller in magnitude than the weight. Again, these 2 add to an overall inward net force. Now this should agree with, if you've ever kind of paid attention to what it feels like to be on a ride like this, this should agree with your experience because you kind of feel heavier as the ride swings to the bottom at the lowest point, right? You feel like the seat is pushing up on you more than usual when you're at the bottom of the ride. And at the same time, when you're at the top of the ride, you feel pretty light. The seat is not pushing up on you with such a big force when you're at the top, and that's what's being shown here. Now, the last thing to do is look at the side. Okay, let's say we're on the very rightmost part of the ride. Okay, we're going to have a normal force going up and a weight going down, and actually these 2 have to cancel each other out. They're just the same in terms of magnitude because there is no net force going up or down. The net force, again, is going inwards towards the center of the circle. The normal force and the weight can't provide that inward force. It has to be coming from somewhere else, and it's coming from static friction. This is the force that prevents you from sliding off of your seat like this and keeps you moving in that circle. Okay? And of course, if we're on the other side, the static friction force is pointing this way. At all times, the net force is going in towards the center of the circle. Okay? That's the idea. So in light of that, we can do some calculations. So this is an example of someone riding on a Ferris wheel. Let's say we have a kid with a mass of 37.5 kilograms riding on a Ferris wheel of radius 12.5 meters, which is rotating at a constant frequency of 7.5 RPM. Now remember, the frequency means how many full rotations or full revolutions does the Ferris wheel make per unit of time, in this case 7.5 revolutions every minute. That's how fast it rotates. At the bottom of the circle, what is the normal force from the seat acting on the kid? And then, as a follow-up, at the top of the circle, what is the normal force acting on the kid? All right, so the diagrams that we showed before are going to be useful here. And in fact, we're just going to sort of copy them. We have the circle that the kid moves in, just like this. And then we just want to show force diagrams of what's going on at the bottom of the circle and at the top. So again, at the bottom we have the weight going down, but a much bigger normal force going up, so that the net force is going inwards. At the top of the ride over here, we have a small normal force, and then the same exact weight from before going down. So again, it's really important to remember the weight just represents the force of gravity. That's not something that's going to change. The Earth is not going to pull on you less or more, depending on if you're on the top or bottom of this circle. The weight stays the same, but the normal force, that can change. Okay, so if we take a look at the bottom of the circle, okay, if we focus our attention on this picture to start off, let's use Newton's second law, F equals ma, but applied for the radial direction, as we've been doing in the past couple lectures. All right, so when we add up forces in the radial direction, you have to remember the sign convention for this. If I have a positive force, that indicates my force is going inwards, and if I have a negative force, that indicates my force is going outwards. Okay? So what we have here is a positive normal force, that's going inwards, and a negative weight, that's going outwards. Adding up to give us m times ar, but as always, the acceleration is given by v squared divided by r for anything moving in a circular path like this. So to solve for n, because that's what we want, we're going to add w to both sides, which gives us n is equal to w plus mv squared over r, and then just remember that the weight is nothing more than m times g. So what we're doing here is we're taking m times g plus mv squared over r. Okay, now we could just plug everything in if we only knew the speed, v, but we don't. What we know is the frequency. Okay, so it's going to take a little bit of work to figure out what the actual speed is. So this is a side calculation, so we can determine what the speed of this person as they move in a circular path is equal to. And just remember that speed is always going to be thought of as distance traveled divided by time. And in this case, the speed is constant, so we don't have to worry about taking an average versus an instantaneous value. It's always the same thing. And if we write this in terms of a formula, what we have is v for speed is equal to a distance. And now I'm going to set this distance equal to 2 pi r, indicating it's a circumference. So the entire distance around the circle is 2 pi r. How long does it take to do that? Well, it takes 1 period. T is the time it takes. So if I could get the radius, which actually I have already, and the period, then I can get the speed. So we don't have the period. What we have instead is the frequency, f, which is equal to 7.50 revolutions per minute. And if we do a unit conversion here to get this in seconds, 1 minute equals 60 seconds. So now we have revolutions per second as our unit. This works out to 0.125 revolutions every second. Now if we take t, okay, that's the period, that's nothing more than 1 over f. Remember, these are the inverse of each other. So I want us to take 1 divided by 0.125, which is exactly 8, as it turns out, 8.00 with 3 sig figs, and the units will be seconds. So this is saying it takes 8 seconds to go in a complete circle if you're riding on this Ferris wheel, which is exactly what we need to calculate the speed, because again, that's 2 pi r divided by the period. And the radius we were given is 12.5 meters divided by 8 seconds. So this is the speed of the rider in meters per second, and it works out to 9.817 meters per second. So now we can do the plug and chug for the normal force, because N is equal to, here, let's copy what we have down there. It's the mass times G plus V squared over R, just taking what we have here and factoring out the M. Okay? So the mass of the rider we were given is 37.5 kilograms. That's the mass of the kid. G is 9.8 meters per second squared. And then we add to that 9.817 meters per second, and we square it. And then we divide by the radius, which is 12.5 meters. This is going to give us the normal force. And it turns out this comes to 657 newtons. Okay, so that's at the top. Or no, that's at the bottom of the circle, sorry. So 657 newtons of normal force if you're at the bottom of the circle. Let's say we're at the top now. And again, all we're doing is taking F equals ma in the radial direction. But the forces look a little different. So let's go to the picture. When we're at the top of the circle, my normal force is going up, which is actually a negative force. It's going out away from the center. And then our W is going down. That's now a positive force that's going in towards the center. So just to repeat that, the weight is going inwards, so that's positive. The normal force is going outwards, so that's negative according to our convention. So we have W minus N, it's the complete reverse of what we had before, equals mv squared over r. So we're going to find N. So we're going to add it to both sides, and then we're going to subtract mv squared over r from both sides. So what we're going to have is N is equal to W minus mv squared over r, like that. And of course, the weight is just mg. So we have mg minus mv squared over r. Pull out the mass, that's a constant factor. And then I'll have g minus v squared over r. And so let's make the calculation. The mass is 37.5 kilograms. G is 9.8 meters per second squared. And now we're subtracting v squared over r, so we have 9.817 meters per second. Square it, divide by 12.5 meters. That's what we have. And if you do the calculation, you're going to find this is only 78 newtons now. So notice, if we compare, there's a much bigger normal force at the bottom of the ride compared to at the top of the ride, exactly as we expected. Okay? So that came out in the calculations. All right, so this is a question for the class. So what I'd like you to do is try to pause the video before, well, read this question, then pause the video, see if you can work this out, then come back to the video, and then see what the solution is. A kid of mass 37.5 kilograms is riding on a Ferris wheel of a radius 12.5 meters, which rotates at a constant speed, just like before. The coefficient of static friction between the child and the seat is 0.5. what is the maximum speed of the ride such that the kid does not slide in his seat at any time? Give your answer in meters per second as well as RPM. Okay. So this is a slight variation on what we just did. Now we have to think about static friction. And if you recall, it's not at the top or the bottom of the ride where we have static friction. In fact, if we're at the top or the bottom, the static friction force is going to 0. But when we're at the side, the static friction force is at its highest value. So let's say we're right here at the side, halfway up the circle, in other words. And what forces do we have? We have the normal force, we have that going up, we have the weight, it's going down, and then we have the static friction force pointing to the right, which is towards the center of the circle. Okay? So if we think about the directions of motion here as being R going to the right and Y going up, just to keep track, what we can do is apply F equals ma in both directions. So let's do it for the Y direction. What forces do I have? Well, I have N, which is up, so that's positive, and then I have W, that's down, so that's negative. That equals, well, 0 because there is acceleration, but it's only acceleration going in this way. There's no acceleration up or down in the Y direction. So at least at this point, it's not necessarily true at other points in the ride, but at this point, the normal force minus the weight is equal to 0. So that gives us N equals W, i.e. the normal force is just equal to mg. Now again, the normal force was not just equal to mg when we were at the bottom of the ride or at the top of the ride, but it is true right here halfway up on the side. So then what we're going to do is the radial direction. The net force in the radial direction is mass times acceleration in that direction. And so the only force is static friction, Fs, and acceleration is v squared over r, just like before. Okay, so we have two things. We have the normal force is equal to mg, and the static friction force is equal to mv squared over r. That has to be true for you to ride in a circle at a constant speed. But at this point, since we're dealing with static friction, we should bring in the inequality which says static friction is not just some constant force. It's given by an inequality, and it's always less than or equal to μs times n. So what we can do then is plug in what we found earlier into that inequality, where static friction is mv squared over r. That's less than or equal to μs. The normal force is m times g. So again, just plugging in these results up here into the inequality, that's what we get. Now I'm going to cancel out the mass. And then the next thing I'm going to do is multiply on both sides by r. So I'll have v squared less than or equal to μs times g times r. And what is this saying? This is saying that if you're not going to slide in your seat, you're just going to have static friction between you and the seat. Your speed has to be less than or equal to some value. So you can't be moving too fast or else you're going to start sliding around in your seat. That's what this is saying. And so we have a maximum speed. Okay, the maximum speed is just equal to the square root of μs times gr. And again, this is saying you can't go any faster than that or else you'll start to slide around. So we can actually put a number to this because we know that μs is equal to exactly 0.5 and g is 9.8. And then the radius is the same as before, 12.5 meters. Okay, so for Vmax, what we get is 7.826 meters per second and that's going to round off to 7.83 meters per second. So that would be the speed, the maximum speed you can be going on this ride, such that you don't start sliding around in your seat. There's actually a follow-up to this, which is find the frequency, okay? In RPM, what is the maximum speed that this thing can be rotating such that, again, you don't slide in the seat? So I'm going to use the result from before, where if we're thinking about speed, that's 2 pi r divided by the period t. And what I'm going to do with this is find the actual period. T is equal to 2 pi r divided by v. And let's plug in what that period is. So it's going to be 2 pi, radius of 12.5 meters, divided by a speed of 7.826 meters per second. And this gives us 10.04 seconds. So that's how long it takes to move in one complete circle when we're going at this speed. If we want a frequency, that's 1 divided by the period. So let's work that out. We make 1 revolution in 10.04 seconds. That's how we think about this in terms of frequency. But we want to convert this to minutes. There are 60 seconds in every 1 minute. So cancel out seconds, and now we have revolutions per minute, which works out to 5.976 revolutions per minute. Or if we round off to the right number of sig figs, that would be 5.98. RPM is another way of saying revolutions per minute. So you can't be going faster than that if you don't want to slide around in your seat. That's the idea. Okay? Actually, I don't know why I'm asking if it's okay. I'm literally talking to myself. So the next thing is drag forces. Drag forces. So when we talk about drag forces, we're talking about the force that a fluid exerts on a moving object. Okay? Whenever you have an object moving through a fluid, that fluid is going to resist the motion. It's going to push back against that motion, and we call that a drag force. Okay? So I want to be clear about the terminology here. When I say fluid, I think typically we think of some kind of liquid, like water, but actually technically a fluid is anything that falls under the category of liquid or gas. So water is definitely a fluid, but so is the air around us. And so the air can exert a drag force on a moving object, just like this. If you take a piece of paper, just sort of wave it around through the air, you can feel how the air is resisting that motion. That force that the air is exerting on this paper is called a drag force. Okay? So what do we know about drag forces? Well, one thing we know is they always oppose the motion. We can say something about the direction of the drag force pretty easily. So if I have an object like this moving to the right, so its velocity vector is pointing to the right, I'll automatically know that its drag force is pointing to the left. It's just going against the motion, much like friction, right? If we had kinetic friction, if something were moving this way, we would say the friction is going this way. The drag force is similar. It opposes the motion. Okay? As far as the magnitude of the drag force, how much force is there? Well, this gets a little bit complicated. So I want to show you guys a simple model of a drag force that experimentally works pretty well in a certain set of situations. Okay? So if we have relatively small objects moving at relatively low speeds, then the magnitude of the drag force is just proportional to the speed of the object. That's the idea. And so again, if you take a piece of paper, just grab a piece of paper off your desk, try this out. Notice that if you move the piece of paper pretty slowly through the air, you don't feel much of a drag force at all. But then if you move it a lot faster, you're going to feel a much bigger drag force opposing your push compared to that. So there is some kind of sense in which the faster the object is moving, the bigger the drag force is going to be. And so we write that as an equation like this. D for the drag force is equal to B times V. Now, V is just the speed of the object relative to the fluid. How fast is it moving through the fluid? And then B is a constant that depends on a lot of different factors, okay? It depends on how viscous the fluid is. So something like honey would be very, very viscous and it would have a very high drag force. Something like the air, the B value would be much smaller. But it actually also depends on the shape and size of the object. So just to show you how this depends on the shape and size of the object, if I drop a piece of paper like this, obviously there's a pretty big drag force acting on it, but if I crumple it up into a ball, same exact mass is there, but it falls much faster. It's much less of a drag force opposing the motion. So that just goes to show that the drag force depends on the shape and size of the object. So this constant B, it's just a number, but it encapsulates all kinds of properties, like what kind of fluid is it moving through, and what is the shape and the size of the object, okay? To get into the details of that is a road I don't want to go down right now, but you can study this in maybe an advanced fluid dynamics class at some point. But for now, let's just say the drag force is some constant times the speed. That's all we need to know for now. Okay, and the reason I want to talk about this in particular is to touch on a topic or an idea called terminal speed. Okay? So I want us to imagine we take some object and we drop it from a very large height and we just let it go, we let it fall to the earth. And we know intuitively, again, that the faster it's moving, the bigger the drag force is going to be. Okay, so in other words, as it falls, it picks up more and more speed, it's moving faster and faster, but at the same time, this drag force, which is opposing the motion, is going to get bigger and bigger. Okay, and this is where we reach something called terminal speed, where the object actually doesn't just accelerate and move faster and faster forever, it eventually just reaches a constant speed as it falls. Okay? And you can see terminal speed in action if you drop something like this. The paper isn't just accelerating down forever, it eventually just reaches a steady speed. Okay? That's terminal speed. So let's look at some free body diagrams of this falling object. And let's start when we drop the object. So this is the start of the motion. So right at the instant when I drop this object, the only force that's going to be here is weight. Because the other force, drag force, which you might be thinking I should put here, is going to be zero. There is no drag force if the speed is zero. So if this is the moment when I drop the object, and it has no speed at this moment, there's no drag force. Okay? It takes some kind of speed for there to be a drag force. So that's what it looks like at the start. But if we start it off this way, it's going to start moving down. And now in the next moment, it does have some speed. It's moving down with some speed. There is going to be a drag force, which is opposing the downward motion. So for now, I'm going to show that drag force as being kind of small because, we're not moving that fast yet. So there's an upward arrow D against the motion of the object, but it's a little bit small for the time being. And then if we let this object fall for some more time, okay, it's going to be accelerating down, so it's going to be moving faster in the next moment, so it's going to have even more of a drag force. It's going to increase as our speed increases. And hopefully you see the pattern. The drag force keeps getting bigger as the object moves faster and faster, but the weight always stays the same. It's just the force of gravity. That's not changing. So at some point, the drag force and the weight are going to be exactly the same in terms of magnitude. Okay? And that's when we reach something called a terminal speed. When the drag force and the weight have the same magnitude. So if the drag force is equal to the weight of the object, Let's think about what that means in the context of Newton's second law, F equals ma. Okay? And actually for this, I'm going to do a little bit of a side calculation on the document cam. So here, let's just switch over real quick. Okay, so we've got a falling object with two forces acting on it, a drag force and a weight. And let's set up our axes like this, x, y, kind of the standard thing we do. And let's take the net force in the y direction to equal m times ay. But the thing is, the drag force carries a positive sign because it's going up, and the weight carries a negative sign because it's going down. And actually, on the other side of the equation, we should be putting 0 here, because now these are equal in terms of their magnitude. Okay? So what we have is B times V is how you write the drag force. M times G is the weight. That equals 0. So B times V is equal to M times G. Again, I'm just saying what we said earlier, that the drag force and the weight are equal in terms of magnitude. So what is V equal to at that time? What is the speed? Well, it's just mg divided by B. And this is a special speed, which we call the terminal speed, because after you reach that speed, you're not going to keep accelerating down, right? There's actually no acceleration anymore. So you don't keep moving faster and faster. Once you reach this speed, that's it. You just keep falling at that speed, and that doesn't change. Okay, so that's the reality of how free fall motion works. You don't just accelerate forever. Eventually, you reach a terminal speed, which is equal to mg divided by b. So it depends on, of course, the object and the fluid it's moving through, but that's the way it's calculated. Now, every object moving through the air is going to experience a drag force. Some objects experience bigger drag forces, others smaller drag forces, but it's always there. And again, because of those drag forces, objects just don't accelerate indefinitely. They eventually reach the terminal speed, and when they reach the terminal speed after that, just keep falling at that same terminal speed. So it's useful to just think about what some common terminal speeds might be for objects falling through the air. Okay? Now the first one on this list is a skydiver. Again, everyone is going to be slightly different as far as what their terminal speed is, but typical value is going to be 150 miles per hour. So if you jump out of a plane, you start falling to the ground, once you reach 150 miles per hour, you're not going to speed up anymore past that. You're just going to keep falling at 150 miles per hour. Okay, what if we took an object like a baseball? That has a terminal speed of about 75 miles per hour, as it turns out. So if you drop a baseball from a really, really big height and just let it fall, once it's going 75 miles per hour, roughly speaking, it's just going to keep falling at that speed. Okay, what about this? A raindrop. Only 20 miles per hour. Now this is a good thing for us, by the way, because raindrops are falling from clouds that are potentially on the order of miles above our heads. So if we didn't have drag forces slowing the raindrops down, they'd be moving at insanely large speeds by the time they reach the ground, and they could potentially harm us. You know, if you have a raindrop falling at 500 miles per hour, you don't want that hitting you on the head. But it reaches a terminal speed, it's only 20 miles per hour, so that's nothing, right? For hailstones, there's a range, because it really depends on the size of the hailstone. It can be anywhere between 10 miles per hour, which is not so bad to get hit with, but 100 miles per hour, that is a big hailstone, and that could potentially hurt you pretty badly. So that's just what terminal speed is all about. And you know, when we talk about drag forces, we're getting at the idea of a non-constant force. Okay? Because as we saw in the example of terminal speed, the drag force kept increasing as the object fell. So it's not just a constant value for the drag force, it's something that changes over time. Okay? So what I'm going to compare is, how does it look like when we use Newton's second law, when we have constant forces, and then when we have non-constant forces? What's the difference? So every single problem that we've solved in this class so far, using F equals ma, has used constant forces. So forces that are not changing in time, just staying the same. Whenever we have that as our situation, when we apply F equals ma and plug the forces in, what we always get is an algebraic equation, meaning it's an equation we can solve just using algebra. And the result, what we get for our solution for A, is just a number. So maybe A is equal to 2.5 meters per second squared. Okay? So hopefully by now we're used to doing this kind of thing, where we solve an equation, it's algebraic, and you just get a number out. Okay? When forces are not constant, they're changing over time, you don't get an algebraic equation, okay, when you apply F equals ma. Instead, you get something called a differential equation. Now, I know most of you probably haven't seen differential equations before. That's okay. My intention is not to teach you differential equations, but I want to give you just a rough sense of what this looks like. So a differential equation, instead of having just a bunch of variables and constants in the equation, instead we have derivatives in the equation. And so we can't just use algebra to solve the differential equation, you need calculus. You need to apply some kind of calculus method to solve the equation. And let's say you solve for the acceleration, you're not just going to get a number. You're not just going to get, A is equal to 2.5 meters per second squared. Instead, you're going to get a function. So A is going to be a function of time, not just some constant number. So here's just an example of what that could look like. A as a function of time is 2.5 meters per second to the fourth times t squared. So this means you plug in a time and you get the acceleration out. Okay, that's how it's going to work if you have non-constant forces. And we're not going to learn about this in Physics 44. We're going to learn how to do this in Physics 45. Okay. So that's it for Chapter 5. I mean, we've done everything in Chapter 5. We've covered all the material, gone through many, many examples. And I think with the time we have remaining in this video, we're going to go through some of the practice problems, not all of them, because there are too many to go over right now. But always keep in mind the answers to these are posted to Canvas, and I'm also going to provide my notes, which have the solutions to these problems. That's going to be on Canvas as well. But since we have a little extra time here, let's go over maybe 2 of these. Okay? So I'd like to go back to some of the friction problems because we've been talking about circular motion for a really long time here. So let's go back to some of the earlier content from this chapter dealing with friction. So this question says, you can hold your 2.5 kilogram textbook against the wall, preventing it from slipping down, if you press your hand against it horizontally. Suppose the coefficient of static friction between the book and the wall is 0.5, and there's no friction between your hand and the book. What minimum force do you need to apply to keep the book from slipping down the wall? Okay, so here's what's going on. Okay, I'm going to take a book, I'm going to put it on the wall, and then I'm just going to push into the wall to hold the book in place. Okay? Now, right now, I'm pushing plenty hard. The book is staying there, and there's no problem. But now I'm going to sort of ease up on the force that I'm applying. And at a certain point, if I don't push hard enough, it just slides down the wall. So we have some idea that there's a minimum force I need to apply to prevent the book from slipping down the wall. That's the idea. So we'll figure out what that minimum force actually is. So here, just to sketch it out, you've got the wall, you've got the book up against the wall, and then you've got your hand. Okay, I cannot draw a hand to save my life, but let's try it anyways. I don't know. It looks more like a foot, but I hope you get what I'm trying to do here. That's pushing against the book to keep it against the wall. Okay. I guess you could use your foot, doesn't matter. So we have the X direction, we've got the Y direction like this, and what we want to do is draw a free body diagram of the book to indicate every single force acting on it. So right away, we have the force P, because you're pushing it to the right, but the wall is pushing it to the left with a normal force. Okay, so that the normal force from the wall is actually pushing it to the left. Okay? There's also the force of gravity pulling it straight down like this. And then there's a static friction force pushing up on the book like this. So you need static friction to keep the book in place. That's actually going up like this. Okay, without this, there's no way you can hold it against the wall. So what we're going to do is apply F equals ma to the X and the Y directions individually. So how about we start with X? Well, we've got two forces. One of them is P, going in the positive X direction, and the other is N, going in the negative X direction. Those are the two forces. What does that equal when I add them together? Well, it equals 0, because the idea is, I'll write this on the side, A is equal to 0, book is not moving. Okay? Whenever you have no motion whatsoever, acceleration is going to be 0. So the push and the normal force are the same thing in terms of the magnitude. That's all we get out of this. If we do it for the Y direction, net force in the Y direction is equal to m times ay. Well, we're going to have static friction going up, and then the weight going down. And then that also equals 0, because we're not accelerating in the Y direction or the X direction. So this gives us static friction equals weight, which is equal to mass of the book times g. So two results here that we're going to use in a second. We're going to put them into the static friction inequality. That's ultimately what we're going to do, where the static friction force is less than or equal to μs times n. What do we say over here the static friction force has to be? It has to be m times g. So sub that in for static friction. Less than or equal to μs. Up here we said the normal force is equal to the force of the push. So I can sub in the force of the push for the normal force. They're the same thing. So what we have is P is greater than or equal to mg divided by μs. Okay, just divide out μs on both sides. This is what we get. And this is saying exactly what I mentioned earlier. In terms of how hard you have to push the book, there's a minimum value. If you're above that minimum value, it works. You can push as hard as you want, and it still holds it in place. But you can't push it too light, because it's going to slide down the wall. The minimum amount of force you need to apply is mg divided by μs. That's P min. So P min is equal to, putting the numbers in now, we have 2.5 kilograms for the mass of the book. We have 9.8 meters per second squared for the value of g. And then we're dividing by 0.5 for our static friction coefficient. This gives you exactly 49 newtons. Okay? Got to push at least that hard. Anything harder than that works. Anything less than that will not work. Okay, so that answers the question. Okay, that's a pretty straightforward example, but conceptually, sometimes it's tricky to set this up, but once you see how it's set up, the math isn't so bad. Okay, so with that said, I'm going to give you an example where the math is kind of bad, and it's a little bit conceptually tricky at the same time. And that's going to be over here. Okay, this problem pertains to the scenario in the diagram below. The masses of the blocks are M1 is 4.5 kilograms, that's the one on the table here, and M2 is 5.5 kilograms, that's the one hanging from a pulley over here. We have coefficients of friction for this block in the table, which are μs equals 0.54 and μk is equal to 0.43. So we have a number of questions. The first question is, if the system is released from rest, are the blocks going to start to move? Okay, so imagine I stand here and I sort of hold everything in place, and then I just let it go. Okay, is static friction strong enough to hold this block here, and therefore hold this block in place as well? Or is static friction not big enough, not strong enough to hold it and starts to move? Okay, so we don't know what the answer is. The second question is, if the system is set in motion so that block 1 is initially sliding to the right, so imagine this. Instead of just holding everything in place and letting it go, I'm going to give everything a push, like this, so that block 1 is sliding to the right, and that means block 2 is moving downwards at the same time. Okay, so if that's the case, what will the acceleration of the blocks be? That's the question. And then will they be speeding up or will they be slowing down? Okay, so we have to answer all of this. So to work this out, let's just kind of copy down that sketch from before for reference. We've got, okay, block 1 on the table, it's M1, connected by a pulley to M2, which is hanging off the table. And so let's get a sense of what the forces are here, and then we're going to use this coordinate system for reference, x being to the right, y being up. So let's draw the free body diagram of each one of these blocks, M1 and M2. Okay, so for M1, here's what we have. We've got the weight, got to label this W1, keep it straight from W2. There's a normal force going up. That's the normal force from the table. We've got tension, which is pulling this block to the right. But at the same time, we're going to have friction of some kind pulling it the other way, to the left. Okay? For block 2, here's what we have here. We have tension pulling it up. And we've got the force of gravity, or the weight, pulling it down. So that's the diagram. We're going to refer to this throughout the problem. Okay? So the first question was about if I release the system from rest, if I hold everything in place and then let go, will it start moving or no? Well, to answer that question, let's start by assuming the blocks don't move. So we're going to start by saying, let's say the blocks don't move. And what do we know in that case? Well, A1 and A2 are both going to be 0. If neither of them are moving, neither of them are accelerating. And also in the diagram where I have a friction force, that's going to be a static friction force, because that's what is happening if this block isn't moving. It's static friction. Okay, so what we're going to do is take block 1 and apply F equals ma. And for block 1, we want to break this down into components, x and y. So let's say the y component to start off. The net force in the y direction is equal to m times ay. Let's apply that to block 1. So I've got the normal force going up. I've got the weight of block 1 going down. And that equals 0 because I'm assuming they don't move for the time being. So the normal force is equal to the weight of block 1, which would be m1 times g. So notice I've got to label everything as being m1 or m2 because both are going to be variables in this question. So now let's do x. The net force in the x direction, we're still on block 1 here by the way, is equal to m times ax, but again that's just no acceleration at all, that's 0. So what we have is the tension minus the force of static friction, tension going in the positive direction, static friction going in the negative direction, equaling 0, which means the tension equals the force of static friction. Okay, now what we're going to do is apply F equals ma to block 2. Now for block 2, we don't really need to think about the x direction because all the forces are vertical. They're all in the y direction, so let's just jump right to that. So the net force in the y direction is m times ay. And that gives us t, which is going up, minus w2, which is going down, is equal to 0 because it's not accelerating. What does that give us then? The tension is equal to w2, which is equal to m2 times g. Now before we said that the static friction force is equal to t. Okay? So that means the static friction force is equal to m2 times g. Kind of makes sense, right? You need exactly as much static friction here to support the weight of this block if we don't want anything to move. So let's put a number to that. M2 was 5.5 kilograms. G is 9.8 meters per second squared. And this works out to 53.9 newtons. Okay, so here, let's just be clear about what this number is. This is friction needed to keep block from moving. Okay, that's how much friction there would have to be to keep the blocks from moving. But the way static friction works is, again, it's given by this inequality. Static friction is always less than or equal to μs times n. So there's a maximum possible value here for static friction, which is equal to μs times n. And n, as we saw over here, is m1 times g. So we have μs times m1 times g for the maximum force of static friction that is possible. Okay? So let's put a number to that as well. What we have is 0.54 for μs, 4.5 kilograms for m1, and then 9.8 meters per second squared for g, which altogether gives us 23.8 newtons. So again, this is the max possible force of static friction. So we've got two numbers to compare. This is how much friction we need to keep anything from moving. This is the maximum you can possibly get. So yeah, it looks like we can't hold we can't have the blocks held in place, right? Because the friction we need to hold them in place can't actually be provided by the surfaces. Okay? So the blocks are going to move. If you release them from rest, they will move because the maximum possible static friction is less than what we actually need to keep them there. Okay. The next thing we're going to look at, and I'm going to try to work this out on a separate paper, but use the same diagram as before, so something like this. Yeah? The next question is, if we set everything in motion where this block is moving to the right and this one is moving down, what's the acceleration of the blocks going to be? Okay. So we're going to let A be the magnitude of the acceleration of both blocks. Because they're connected by a string, they're going to move together. So if this one is accelerating at 1 meter per second squared, so is this one. The A value is the same. The magnitude is the same. But, of course, the direction is not the same. This one can accelerate either to the right or to the left, and this one can accelerate up or down. So they're the same in terms of magnitude, but we got to get the signs right when we work this out. Okay? So here, let's start by saying this. Assume block 1 accelerates to the right. So if I have block 1 accelerating to the right, that automatically implies block 2 is accelerating down. Okay? Now, we might be wrong about this. It might be that actually block 2 accelerates up, then block 1 accelerates to the left. But it turns out if we're wrong about this, then our A is just going to come out with a negative sign. Okay, so we're going to do the problem assuming it works this way, where M1 accelerates to the right, M2 accelerates down, and then we'll see if that was the right thing to assume depending on how A comes out. Okay. So we've got block 1. We're going to do F equals ma on block 1, but this time we're not going to set the acceleration to 0. So what do we have? We have the tension force going to the right in the positive direction. We've got now kinetic friction, because it's sliding, so there's kinetic friction going the other way. And that equals m1 times A. Okay? So what can we do with this? Well, we can remember how kinetic friction works. It's equal to mu k times n. And actually, we found earlier that the normal force is just going to be m1 times g. So I'm just going to make that substitution since we already figured that part out. And this is going to give us T minus mu k m1g equals m1a. So what I'm going to do with this is just solve for the tension. It's m1 times a plus mu k m1 times g. That's the tension. We got that by looking at the analysis of block 1. So now we look at block 2. The net force in the y direction is m times ay. Because again, all we have are forces in the y direction here. One of those forces is tension, which is going up. That's the positive y direction. The other is weight, which is going down, so it has a negative sign. And that equals m2 times the acceleration of block 2 in the y direction. Now we have to be careful, because we're assuming block 2 is accelerating down, so that needs a negative sign. If I want to indicate that the acceleration is going down, ay has a negative sign, so that's where it is. And actually at this point, we can make two substitutions. Right here, we can plug in our expression for the tension that we got just a second ago, which is m1 times a plus mu k m1 times g. And then I'm just going to subtract right here the weight of block 2, which is m2 times g. That's going to equal negative m2 times a. So guys, I hope you can see that for a problem like this, where there are a lot of different forces to consider, there are two moving objects to consider, you really have to be careful about how you set up your equations. Okay? But if you recall, what we're trying to solve for here is the acceleration. So here's what we'll do. let's put on the left side of the equation every term with an A in it, and let's put on the right side every term with a G in it. Just separate those out. So I've already got m1 times A on the left side. If I add m2 times A to both sides, now it's over here on the left. Okay, I'm going to add m2 times G to both sides, which puts it over here on the right. I'm going to subtract mu k m1 times G from both sides, which puts it over here on the right as a negative term. So let's write this one more way. We have m1 plus m2 multiplying a common factor of A. And then over here what we have is m2 minus mu k times m1 multiplying a common factor of G. So if we want to solve for A, we're going to have m2 minus mu k m1 divide by m1 plus m2, so divide by what's in parentheses here, and then that's all multiplying a factor of G. That's going to give us A. Okay, so m2 was 5.5, mu k was 0.43, m1 was 4.5, and then here we're adding 4.5 plus 5.5, and then we have 9.8 meters per second squared. So we get our acceleration now, which is 3.49 meters per second squared, but we're going to actually keep 2 sig figs, which rounds to a nice 3.5 meters per second squared. Okay, so notice this came out positive, and the fact that it came out positive means the directions we assumed, that block 1 is accelerating to the right and block 2 is accelerating down, it means that was correct in what we assumed. If it was incorrect, this would have come out negative. But what does it mean? Okay, so there's a question about whether things are speeding up or slowing down. So if I have block 1 moving to the right, its velocity is to the right. Here, let's just draw that. V vector is to the right. And also at the same time, its acceleration vector is to the right, which is what we just found. Then it's speeding up, right? If velocity and acceleration are going the same way, the object is speeding up. So we can just write that last bit. It is speeding up. And that answers the whole question. Right, so we're going to just leave it right there. That's the end of chapter 5. I hope everyone's staying safe and healthy out there. Again, this is kind of a strange and uncharted territory for all of us, having to move the class online with such short notice. So again, I want to say thanks for just being patient and being able to adapt to all these changes we're making. So yeah, I look forward to when we can all have a class in person again. Until then, I'll see you.